Okay, let's get started. Just a couple announcements. I have asked you to define classicist, fiducialist. Oh, what did I put down there? Did I put down likelihoodist? Not there. So whatever these definitions are. Fiducialist, Bayesian, frequentist, and classicist. What I want you to do is hand in a piece of paper with about 3 or 4 sentences per. Try to be concise. You know, rambly definitions, you know, that go on for pages and pages just aren't good enough. We're all supposed to be statisticians of some sort. So when you're hanging out with your friends and they say, what's a Bayesian? You're supposed to tell them what that is in about 10 seconds. So you don't have 10 minutes to tell them. So, real quickly, what's Bayesian? See if you guys can do it. So when he comes up to you, I'm sure you've been asked this question. I hear professors get asked this and they go on for the 20-minute definition. It's like, whoa. Now everybody's totally confused. But can you do it in 10 seconds? What's a Bayesian? Okay, allow me to let you use a technical definition. If you use some technicalities. I usually like my definitions in kind of plain English. So I can convey it to somebody. Here's what we're trying to do with it. So, say you're allowed to use a technicality. What's Bayesian? Oh, wait.
You have prior belief or something, and you base on your prior belief to estimate something.
Okay, so maybe something like that. That's the Merriam-Webster. I'm allowed to use my prior beliefs. I don't love the definition, but thank you. You know, and so you get stuff like, well, doesn't everybody use prior information in doing things? It's how you use it. If you were to be technical, you'd say every Bayesian is doing likelihood times prior, at least conceptually. So they have a likelihood function, they multiply it by some weighting function, the prior. I usually say, if I'm going to use a technicality, something like a Bayesian is somebody that does inference based off the posterior distribution. Now, what is the posterior? It's proportional to the likelihood times prior. So these are definitions you couldn't just say to somebody at a party. You'd have to start writing things down. But I might say a Bayesian is the one that puts the probability distribution on the unknown quantities. And that's what a Bayesian is trying to do. They're trying to put a probability distribution on the things you don't know. So conditional on the data. You know the data, you got to see it. And so what are the things you don't know? Probably the parameters. So they're putting the probability distribution explicitly on the parameters. And somebody at the party would say, why wouldn't you do that? Isn't that what you want to do? And I would say, yes. It's that appealing. It's just appealing. Put the probability distribution. Use the probability as a descriptor of the things you don't know. How do you get there? You need to use Bayes' theorem. And so a lot of people use Bayes' theorem. They're not putting the probability distribution on the things they don't know. Bayesians will do it with anything you don't know. The parameters. Let's say you have missing data. They'll end up building a posterior distribution along on the missing data. And they have joint inferences between all the things they don't know. So I think a Bayesian gives you 2 good things. Joint inferences, probability distributions on the things you don't know. The joint part is important. How do things co-vary together? How are they co-uncertain? And you have auto-regularization. We'll talk about regularization later. But penalties are usually a good thing to build into your models. And so Bayes gives you a mechanism for that. Try to say something in a sentence or 2. What's a classicist? That's my favorite one for you guys to try to define. Because a lot of people walk around and they're like, I'm a frequentist, I'm a classicist. So what's a classicist? You know? Anybody have a definition of that? Anybody into literature? What's classical literature? What does it mean? Somebody says, I'm into the classics. Okay, popular, so like J.K. Rowling. Yeah. That's the classics, right? Yeah. Harry Potter, it's pretty popular stuff. Tom Clancy, popular. Classics. You don't mean that. Right? So yeah, they're a little bit like, to talk about them, they probably have to be popular. And so to be still talking about it, I just gave away a hint, to still be talking about it, they must have been popular. So all the classics are popular because they were popular, but they've endured the test of time. Has something to do with the time part. For something to be classic, it has to be old. This is not well defined. classicism. Bunch of old stuff. The stuff that we used to do for a long time. So what was Fisher doing? He wasn't always a frequentist. He wasn't always a likelihoodist. Sometimes he was a fiducialist. And later on, he admitted to being a Bayesian. Confused things even more. So there's a lot of overlap between these things as well. But this class is supposed to help you to answer the question. So let's start with the end in mind and try to answer it now. And later on, you can see how your definitions update as you get more and more data. So that's meant to sound big here. Okay. So try to define those. I've also given you a few homework problems. Maybe we can do a review session next Wednesday before the homework is due on February 7th. So these are just some teaser problems and see how your probability is doing. So a whole bunch of lessons to be learned in all these problems. How many people are still trying to add the class? I think nobody should. So we opened up a whole bunch of new seats. And the price I had to pay for this was to get a new room. And I apologize to you guys because I can see we have a couple seats open. We always get 5 or 6 people that don't show up to class. So, but I technically cannot host you in the class unless there's a seat. And so, why is that? Well, it's because the fire marshal comes and talks to Betty and then Betty talks to me. And so, I ended up needing to get our room across campus. It's going to be in Williams, 320. So we're going to be starting to have class there on Wednesday. So new room. WMS is the abbreviation, 320. So same time, different place. So that's where we're going to move. I got about 8 more seats and I was able to satisfy all of you, hopefully. If you weren't able to get in, and I don't think that's anybody here, that's not my fault anymore. So I'm going to stop trying after this. So today is technically the last day to add as well, so get in on that. Anyway, I apologize to all the stats students because I know your office is there. And so mine is too. So I have to walk across campus as well. There'll be a couple blustery days. It's not going to be all that great. 10 minutes of trouble, no big deal. Okay, so new room, more seats. Okay. I think that's it for the preliminaries. Just so you know where we're going in this class, I'm going to ask you basically read through 5.1 through 5.3, try to understand what it's saying because I'm going to be lecturing on those. I'm going to be talking about nuanced topics like sampling with replacement and without replacement, just like the book does, but I'm going to motivate a technique as we do this. So I'm going to jump straight into bootstrapping. And so in the book, they have one sentence and they say, sampling with replacement, is a useful technique in bootstrapping stuff. And if you've ever seen this algorithm, it's super simple. I used to not like it because it was super simple and I couldn't bedazzle anybody with mathematics anymore. It's just this process, this procedure. There's some assumptions that have to be true for you to use that tool effectively, but we're going to jump straight into bootstrapping. Then I'm going to introduce to you things like the central limit theorem. That's in 5.5. And we'll be talking about a lot of the properties of data themselves. We'll also be talking about order statistics and all that stuff in Chapter 5. Chapter 5 is going to take us a little while to get through. So I would just start reading now. Maybe up to 5.3 by the end of the week and you'll be in really good shape. Okay. I want to get back to this problem where we're trying to infer theta. That's what this class is about. So I don't expect you to be able to do all the mathematics we talk about today. I want you to understand where we're going with this problem. By the end of this class, you'll be able to answer this question really concisely. And you'll have lots of reasons for why you pick certain thetas. But let's just jump ahead a couple months and see some of the estimators we could write down. So we did this last time and we wrote down a whole bunch of estimators. So this is the truth, and just for notation, this is an estimator. Somebody tell me what an estimator is.
It's a quantity that's a function of the data.
Yeah.
That's supposed to be a good estimate of parameter.
Yeah, so it's like now we need properties to say what good means. So what is good, but it's a function of the data. And hopefully it's got some good properties that it's kind of around this. And around this can mean different things, either in terms of it varies right around it, it could be unbiased, maybe in distribution it's squeezing down to it, maybe the rate at which it's squeezing down is the difference between these estimators, but as we'll see in a second, there's a lot of different properties for estimators. But this is a function of the data. Function of x, which is just all of your data. Given theta, I've got a vector of n data points. And so this is never a function of theta itself. So I'll just put a note here, because this is the worst mistake you can make in this class. Not a function of theta. So let me just nip that one in the bud right now. And so you give me estimators that I need to use theta to use. It's not a good answer. If you knew theta, you would just use it by itself. Okay, so we had a couple choices. So we wrote down a bunch of different estimators. So let's just entertain a few. Let's say theta hat 1 is equal to the range. I'll just write down like this. Xn minus x1. Let's see, this is the range. And then we had some other ones. Theta hat 2. I think we said xn plus x1 over 2 times 2. So this is just the mid-range times 2. We wrote down a whole bunch of them. Let's just use the same order. I've actually coded all these up. We'll experiment with these via simulation. Let's see. Okay, I like this one as well. Theta hat 3, and I said x bar times 2. So x bar is just the sum of the xi's divided by n times 2. So both of these, the mid-range measures something in the middle, and I'm just multiplying it by 2 to push it over to the boundary. Say that's a good estimator of theta, and this is very similar. It's measuring something in the middle. It's a different point, presumably, and I'm multiplying it by 2, but they're about in the middle. And then we wrote down a few weird ones. We wrote down this one. Thank you, Ben, for this suggestion. So this was the R minimizer over theta of this least squares problem. So I'll say I times theta over n. I'm going to subtract that from the order statistic. These are order stats. So just to be clear about that, using the same notation, the xi's themselves are IID from this distribution. So they're uniform data points over this. If I put the brace on it, I'm ordering everything. So I just order that vector. This is going to be the maximum order stat. Max of x. This is going to be the minimum of x. And x2 brace is going to be the second biggest thing. So these are all the ordered points right here. And if everything was perfectly uniform, if those points were actually perfectly uniformly placed on a grid, and I chopped up the grid uniformly, these points would kind of hover around those grid points. Okay, so these are estimating the quantiles of the distribution. This is empirically what we see. That's not always true for any order stat. That's true because this is uniform. And so I'm taking that uniform property. So these are just the quantiles. Theoretical. So the 90th quantile is, 90% of the data is to the left and 10% is to the right.
So would the expectation of the order statistics in this case be the quantiles?
Yeah, we'd have to see that. Yeah, so we might want to, expectation is kind of a funny thing. And so sometimes yes and sometimes no. In this question, you'll be able to answer that in a couple days' time. And so maybe that's a good homework problem for you. And so, but it depends on the distribution at hand. So expectation is a funny thing. They're going to be around it. So you'd expect. So using the same language. You have to be careful. It depends on the distribution at hand. But Mohammed is asking a question is, what are the distributions of the order statistics themselves? And so the distributions of the order statistics, once I order everything, are totally different than the distribution of the data points. Okay, so let me just be clear about that in a picture. So if I ended up sampling n data points uniformly from this distribution, so this is just going to be theta here, 0 over here, 1 over theta, I ended up seeing a bunch of data points. They don't come out ordered like that. I just drew them like that. So this is going to be the nth order stat. That's xn right here. If I did this again, so I ended up getting n more data points, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Drew 15 more points. Theta again is over here. This is where xn lives this time. It's not going to be at the same exact point. It's going to be somewhere different. And so if I look at the distribution of this, if I just did it over and over again, I'd expect the nth order stat to be somewhere around here. Where do the xi's land? The xi's land anywhere in here. But the nth order stat lives somewhere over here. And so to understand these estimators, we have to understand what these distributions of the order stats actually look like. Now, fast forwarding a couple pages, they show you what the distribution of the order stats look like, the co-distributions, the joint distributions of order stats. Read through that soon. I'm going to show you how to derive those formulas in a very intuitive way. So in the book, they kind of go on in an argument with a paragraph with a whole bunch of math buried in the paragraph, and then they say, voila, here's the distribution. It's a little bit of a hard way to understand it. But I will tell you, if you did know the distributions of these, the distributions of the order stats are just some transformation of the original data points. And so knowing this distribution, I could answer the question, what are those order stats? And in this example, you can write it down in closed form. And the question that Mohammed's asking is this point right in the middle expectation, if I took it, for that distribution equal to that lattice point, that last lattice point on the uniform grid? And come to my office and you tell me the answer in a couple days. About 15 minutes worth of calculus. So this was kind of a neat thing. We ended up getting this answer right here, that once we've done calculus on this whole thing, all I have to do is take a derivative with respect to theta. We did it last time. And set everything equal to 0. And as soon as we set it all equal to 0, we throw a hat on top of our thetas. So that was a procedure that we're using. And so it turns out that this answer looks like this. I over n xi divided by sum of the I over n squared. Again, take a derivative with respect to theta, you're just rolling through the chain rule, and this is what we ended up coming up with. So this was our answer. So this is Ben Beach's estimator. What do you think, Ben? You like it? We could write it down, that was cool. Okay, let's just write down one more estimator too. Theta hat 5. I'm going to say this is going to look like this. Some number times the maximum. So this is a scaling factor on the maximum. Okay, so I'm going to take that maximum and I'm just going to budget around by some scaling factor. Is that a good idea? What do you think C should be? Bigger or less than 1?
Bigger.
Bigger, yeah. Because xn always lives to the left of theta. And so we need to budge that thing. It turns out, I'm going to call this thing a Bayes estimator, but there are a lot of ways to estimate this. Let me just tell you what I have in mind. And I'm going to give you a couple different options in the code. So for theta 5, I'm going to call this a Bayes estimator. And I'm going to be explicit using this particular prior. So 1 over theta raised to the k power. I just write this down up to proportionality. If k is 1, that doesn't integrate between 0 and infinity. And so it turns into the logarithm, evaluate the logarithm, at infinity, and that's going to blow up. And so if k is bigger than 1, then this prior integrates, and it's proper. And I could come up with a normalizing constant for it. So what this prior is saying, that if I pick big values of k, then I'm smushing theta down towards 0. I'm saying don't let it get too big. So I don't want it to be too huge of a number. So a prior, we're saying that. And so it's called a power prior. We'll be looking at this analysis soon, but for certain values of k, we're going to get forms like this out of the posterior expectation. So I'll take my likelihood function, I'll multiply it by this prior, I'll do my calculus, I'll come up with the expectation, and the expectation is going to have this form, where this right here is going to be a function of k and n. And it's going to be pretty smart. It's always going to make it bigger than 1. So we're going to use all the information in our description of the distributions to come up with it. And so there's some really good choices in here as to what you want to pick for C. We'll examine a few of them. I'll give you a heads up real quickly. I can use k as a knob to change the properties of my estimator. So I could, for certain k's, I might be able to say this is an unbiased statistic. Different values of k will give me different values of C. Okay, so I might say, I want to use that as a knob to get a statistical property. I might say I want to minimize mean squared error out of it. It turns out when k is equal to 3, you're going to minimize mean squared error. When k is equal to 2, it minimizes bias in everything. Which one do I like doing? Well, I like being closer on average. So if I thought my loss function was squared error, we have to talk about that. What does that actually mean? Then I would end up with my best answer would be derived from k is equal to 3. Lots of math we have to learn to understand how all that works. What does it mean to actually be a Bayes estimator? We're at least a month away from answering that question. But you get the basic idea. Some of these answers look kind of appealing. Let me just say a few more things about them. So I've got a collection of estimators that we've kind of just come up with in our head. And we want to answer which one is best out of this. We might want to answer, is the best solution overall amongst these 5? And we need a lot of theoretical tools to be able to answer that question. But which of these answers do you think is better? Just guessing. You can be educated in your guesses or not, just intuitive. Who knows? Which one do you think is best out of those, or better, and why?
Number 5.
So 4, 5, okay, I heard both of them. Anybody like this one? This sucks. Why?
It's always wrong.
It's always wrong, it's guaranteed to be wrong. So we know that xn, the max, x brace n, order stat, is always to the left of theta. Now I'm going to subtract something off and pull it even more to the left. Oops. So even though x1 is estimating 0, but it's going to be positive. And so this one looks like it'll probably be a little bit better. So because it's adding some noise to it and budging it towards it, like, is that the right amount to budget? Why should that be the right amount? Maybe, I don't know. So there's reasons to think that this little budge of something, you know, is a good idea. So this is kind of an additive shift, where this one is a multiplicative scale of everything. What about this one? Is that good? Maybe. We see X bar come up all the time. What's that?
It could give you something less than the max.
Could be. Could be. So, could be good. Maybe. There's at least reason to think that it could be good. But let's think about something real quickly. What do I know about theta? I know it's always bigger than the max. Guaranteed. So, theta's going to be bigger than xn. Why? Because of my picture over there. So theta is always to the right. Data point's always to the left. And so, question is will this estimator always give you something that's bigger than the maximum?
Not necessarily.
Not necessarily. And we know that that's a hard constraint. We should be following that rule. And we're violating it by using this statistic. It might be okay, but there's reason to think that this could be improved. What we like about this estimator is I know what the distribution of x bar is, about. If n were big-ish. What's ish? Not too, it doesn't need to be too big. So maybe like 12. They say in like your Stat 101 book, gotta have 30. We're gonna forget that rule real quick. So it absolutely depends. 30 is not enough to say this is normally distributed. I have seen in some textbooks that say we use 31 in all our examples to assure normality. And yeah, it's really repulsive. So that doesn't assure you anything. So we want to forget some of these basic rules. We want to be able to check them in this class, see if that is a good rule. And so, but we know what the distribution of that is about. It's about normal, so I can start doing analysis on this thing. It's hard for me to figure out what the distribution of this is if I don't know the distribution of the order stats. And this is a transformation of the distributions of the order stats. It's a difference between two non-IID distributions. These are not identically distributed, xn and x1. xn lives over here, and x1 lives over here. And so I need to figure out how to take that difference. If you've taken probability class, you can do it. No big deal. But to formally analyze this, we need to figure out what those distributions are. This one right here got a little bit of favoritism from you guys. So I think maybe one of the answers is that I might be able to say, well, I like theta 4, it's good, for 2 reasons. Ben came up with it. Ben's always coming up with good stuff. So, sometimes. So, one thing to say about it is it uses all the data, right? So it uses everything, and that's good. And this one, it uses everything. Not throwing everything away. Is that fair to say, David?
I think the order stages also use all data.
Thank you. It does use everything, right? So the order statistic, I needed everything to order it in the first place. And so these statistics do use all the data. Just doesn't look like it, but you can't order everything without everything else in place. And so elusively, these are using all of the data, all of them. Maybe this looks cool right here because, I don't know, I had to do calculus to come up with it. I had to do some math. Took a derivative, set it equal to 0, solved for that solution. And I kind of like this solution. It makes sense to me. It's a weighted average of the order statistics. And I'm putting more and more weight on everything as I start marching through n. So I'm putting more weight towards the maximum. That feels kind of cool. Less weight over by the minimum. Feels good. So kind of like it. Let's just look at the asymptotics real quickly of this. I like to investigate this before I show you answers. So again, we're just getting warmed up. I can take this n and put it over here, right here. So I can factorize that n out. There's n squared down here. Okay, so there's n squared things. What does some of the I squared look like? You guys know.
It's the physical divided by 6.
Yeah, there's some answer to it, right? And Gauss could have told us what it was when he was 11 years old.
Some of an arithmetic sequence, like the squared arithmetic sequence.
Yeah, I think it's this. N times n plus 1 times 2n plus 1 divided by 6. When I saw this, I was working through Ben's suggestion, sitting on my couch, and I'm like, what does that sum equal to? And I just grabbed my calculator real quick. So I actually pulled out my calculator. I remember seeing this a long time ago. And then I saw the little proof to it. I was like, oh, that's cool. So, but anyway, this is cubic. Okay, so this is all cubic right here. So the I squared is, some of the I squared is a cubic term. And I've got a quadratic term and a linear term, and they are all canceling each other out. So asymptotically, the n's disappear. Asymptotically, if you buy my argument, they do. N gets big, and there's a factor of 6 that shows up here. That factor of 6 certainly is going to blow up the variance on us. So that 6 factor is going to get thrown up here, upstairs, and then when I take the variance, I'm going to have a 36 multiplier. So, shucks, and it never disappears, so I'm stuck with this variability. But there's something even worse that happens. So I'll say this limits to just this thing. 6 times I xi. A little bit of math. I have no idea what the answer is, so I'm just looking at formulas like you guys are. But I look at this thing and I know this multiplier right here being 6 is going to increase the variability quite a bit on everything. And then I'm going to have the variability attributed to all of these xi order stats. They're never going to go away. And I start seeing more and more data in the formula. Uh-oh. That variability just keeps getting bigger and bigger and bigger because I keep adding in more and more stuff. So throwing in all these ordered points kind of hurts you. So that's kind of interesting. So, but it's still an estimator. Still kind of does something. Let's go to the computer. So we learned last time that Pearson and Fisher disagreed mathematically on something, and Pearson, regardless of human rights violations, I mean, these people got paid. So had 30 people sit in a room and crank out contingency tables to answer some mathematical question. I'm never going to test you on the test of independence. It's not important. It was just a concept. So if you've seen that test, great. How do you answer what is the correct degrees of freedom? Well, you've either taken the class and somebody said it's obvious that it's this, and you just believed them, or you ended up working out a lot of mathematics. Fisher and Pearson were pretty good mathematicians, and so they couldn't agree. So Pearson went to his computer and score 1 for Pearson. And they volleyed back and forth. What was the score at the end of it all? I don't know. We're all the worse for it. So, okay, so I wrote this piece of code. It's pretty simple. Let me show it to you. So I've got a bunch of replicates and things like that. A is my theta and everything. I just didn't want to spell out theta throughout the example. So let me just make sure you understand. This is A. My A's and alphas typically look the same. So theta is A in my code. So N is the number of samples we get for each thing. And I'm going to repeat this process 1,000 times. So what I'm going to be doing is I'm going to be building up the distributions of these statistics just by building a histogram. Is that big?
I just can't read any of the words back here.
Oh, I gotcha. I see what you're saying. Well, next time I'll make the font bigger. Okay, so we've got a bunch of different statistics that we're collecting. So for each one of the replicates, here I've made 2 replicates on the chalkboard. I can't draw this out 1,000 times, but I can use my computer to do it 1,000 times. And so I'm going to collect a data set. So this has n uniformly distributed points between 0 and A which is theta on the board. And so that's a data set. Right here, rand is my uniform random number generator. Then I form the range, 2 times the mid-range, x bar, do something like that. I'm going to multiply by 2. We'll make sure I do that in my code. We'll multiply these 2 things by 2. Then I'm going to compute this thing right here. This for me is just kind of weird because I'm regressing on the quantiles in a least squares sense. So I'm losing all the good properties about quantiles by regressing in a least squares sense. So it's actually trying to regress towards the mean of the quantiles, which is weird. So you might appreciate that at the end of this class, that it's just weird so to do that. But maybe it's a good estimator. So here's what it is. So it's just a weighted average. My weights are just this, the I over n's, and I can code that up using this linspace command or a number of other ways. And this thing that I'm calling it Bayes estimator right here, and I've scaled it by a number of different scaling factors, so we can change that if we want. And so I've got n plus 1 over n, slightly bigger than n. These all come out of various solutions to using k being different numbers. And I can derive this one as well. I think this goes hand in hand with k is equal to, this one's k is equal to 3, and this is k is equal to 2. So this turns out to be theoretically unbiased. And this one turns out to be theoretically lowest MSE. What am I going to do with all of these things? I'm going to plot those 1,000 replicates. And I'm going to try to learn what the distribution of those test stats are. So we'll see that all work. And then I'm going to plot out for you the mean squared error. So MSE is just this function. Mean squared error. So we first look at our errors. Our errors look like theta, and I've got my replicate function. So I goes to the number of replicates. And so this is going to be theta hat, I'll write it down as I, minus true theta. Square that thing, and then take the mean. So this is a game I get to play in theory. With real data sets, you can't do this, because you don't know what theta is. But in my simulation, I do get to know what theta is. So this is a tool for answering questions about this particular setup of the problem, with this particular n and that particular a. And so we need to change those around a little bit and see how the solutions change. So let's just start with a is equal to 1. And I'm going to get n is equal to 20. I'll get my 1,000 replicates. I'll plot histograms of all of my estimators. And then I'll compute the MSE for you. So let's run it. So here's our answer. So what I did actually, we're going to come back around to this picture later. This is drawn in your book, I think around 5.3. This is just the distribution of the paired mid-ranges and ranges. So I've got the mid-range and the range, and I plotted them together. And there's this weird triangular shape that comes out of it. I want you to think about that triangular shape. There's a good picture and description of it in your book. Let's forget about it for now. But here are my histograms of all of my estimators. That's what they all look like. So my 1,000 replicates for my first estimator, the range, are plotted right here. All of them are plotted. And so if I ran this a whole bunch of times, if I cranked up the number of replicates to like a bazillion, these histograms would get very smooth. And I'd be getting closer and closer to the true mathematical distribution of those estimators. We knew how to do it. And so this is what we get. So the range is always budged to the left. Sometimes I get really bad answers, 0.6, where I'm always supposed to be estimating 1. So this one at least overlaps 1 in kind of a nice way. That's pretty cool. But I've got a lot of variability in the answers. So this one also overlaps 1, 2 times x bar, as we expected that it probably would. But there was a lot of variability. Sometimes I come way out here over by 1.5, and this estimator doesn't go out that far. So if we look at the ranges on the x-axis, we can kind of see that we don't want to deviate too much. Here's some answer right here. So the least squares, quantile regression, a lot of variability. These tails look pretty chunky. So a lot of answer in the tails. We want this thing to be peaked. And then here's the Bayes answer. And this one doesn't look very uniform or symmetric or anything like that. It looks kind of weird. But it's a lot different than this answer. This one's always to the left of 1. If we look over here, this one puts a ton of mass right to the other side of 1. And so is that a good answer? And I would say, yeah, I probably want to err on the other side a little bit because I always know theta's bigger than my max. The Bayes estimator deals with that just fine. If I look at the MSEs, I've got pretty comparable mean squared errors. I got 0.01, 0.00, 0.02, 0.01, 0.00. Probably need some more decimal places to try to compare those two things. But it seems like it kind of doesn't matter, and I'm going on and on about stuff for no good reason. What I've just said is you can kind of use anything, as long as your error tolerance is about 0.01. So, and they'll all be within that.
What does the histogram of the k is equal to 3 Bayes estimator look like?
It's this one. Oh, I did the other one, right?
Yeah.
Okay, we'll look at it in a second. So let's look at it in a moment. I'll comment that out. We'll change it. It's a good question. But all kind of comparable. Let's change some numbers in all of this. So I'm going to crank this number up, 10. So A is 10. Do I have the same information about everything? I still have the same number of data points. I've got 20 data points. So if I change any asymptotic properties, the behavior of all this stuff, wildly, I have. Because now I've changed the sparsity level of the problem. So I have this bigger interval, and I still have the same number of points inside of it. And so I'm not covering the true distribution very well. And so learning about the true distribution requires that I cover it. And so I've dramatically changed the properties of this problem. Let's run everything again. That's what I come up with. Similar picture. And here are my MSEs. 1.33 for the range, 0.38 for 2 times the mid-range, 1.71 for 2 times the mean, 1.17 for the quantile thing, and this scaled maximum, which I'm calling a Bayes estimator because I can derive it via Bayes' theorem. I know there's some non-Bayesians that go, I can derive that without Bayes' theorem. So that's not a Bayes estimate. Well, it is. But there's a lot of ways to skin cats, a lot of ways to derive things. We like skinning cats in this class, so we skin a lot of them. We do things a lot of different ways if you don't know the metaphor. So it's actually quite feline friendly. So Bayes estimator seems to do pretty good. Let's look at a couple more.
What was this measure again?
This one's 0.19.
No, I mean, what are we measuring again? MSE?
The MSE,
Right.
yeah, mean squared error. What am I assuming when I use MSE as my diagnostic tool? There's assumptions. Why didn't I make this absolute? it's not going to change the ordering of the problem, but it's all about how you're thinking about the errors you make and how you want to penalize yourself. So we're assuming squared error loss function. So farther away from the true answer, I'm penalizing myself harder than if I used absolute. We'll talk about what that all means later in the class. And so this bottom thing, the Bayes estimator did pretty good. Let's change the problem a little bit more. Let's change this to n is equal to 200. Asymptotics maybe should be about the same because I've multiplied now both the endpoint and the number of data points by 10 from the original problem. So maybe we get something similar to the original problem. Turns out it's not true. So the range, 0.02, the 2 times mid-range is about 2 times better because it's half the size. 2 times the mean is quite big in relationship to those. And the MSE of the quantile least squares estimator, not a quantile regression estimator, 0.10, so pretty close to that one, and the Bayes estimator is 0.00. There is error that's being incurred. We can see it in the histogram, but it's not too big. And so that's kind of amazing. And so one of the things is can we theoretically convince ourselves that's a better estimator? We can certainly do it in the simulator. So can I convince myself that's the best estimator on the block too, that I can't go out and come up with a beta hat 6 that does better? Mohammed?
It seems to me just like visually that the mid-range, the second estimator, would be better if we had used absolute error instead of mean squared error, because it seems like it's getting a lot further off than the Bayes estimator.
I'm going to tell you this. These will be ordered the same, but you're right that maybe that deviation doesn't yank the diagnostic that far out. So, but you can play around with it if you want. I'm going to put this code online so you can go and change those little functions. So if you want to change this, you change the MSE thing down here. So instead of squaring out everything, just put abs right there. So I'll post this online. You can play around with it and see what's going on. But the Bayes estimator is pretty well behaved. Let's just do a little bit more. Let's just make this a little bit bigger. 100, and multiply that by another 0 on the sample size 2. So everything got multiplied by 10. Run that again, still pretty fast. And we notice there's a big discrepancy between some of these estimators. The range and the mid-range got pretty good. That X1 started estimating 0 really well because I cranked up the sample. So it started squishing those things down towards 0. And these things got pretty comparable to each other. This one's horrible, 2 times the mean, even though the central limit theorem is kicking in really well for us, it's not helping us a lot. Still a decent estimator, but compared to those, they're not even in the same ballparks. The Bayes estimator is still the champion. And so there's principles that tell us that the only piece of data we should be touching is that. So when we study the sufficiency principle in chapter 6, we'll learn we should only touch this. What we do with it, the sufficiency principle doesn't tell us. It depends on how you want to operate inferentially. Do you want to be a Bayesian? Do you like the on-average properties of doing really well? And in a simulation study, that is what we're measuring. And so are there some other properties that you want to induce? And so can I use that prior to do it, or do I need a different prior? And that's what we're going to learn in this class. Any questions about this before we start picking up with more book-oriented work? So I'm going to start carving through the book. We'll go through 5.1, 5.2 next time, and build up to the bootstrap. But you guys could all repeat this, and hopefully you understand the take-home message that the way we use the data greatly affects how well we do, even though we all have estimators for something. So, and those estimators have different properties depending on what the parameters are that actually drove everything. And N is a big influencer as well. So that's what you're supposed to be thinking about so far. We'll get into formal theory next time. All right, thanks you guys.